Here it comes. Well, doggone it, gentlemen. Hats versus bald heads. Once again,
Hey,
it's
man, I
time.
got hair.
Hello, everybody. We're doing it. We're on live, at least live at the moment, and we'll be in the future recorded for watching. Our special weekly vlog is underway, 11 to noon on Mondays, the SBAU Astro Hour. On behalf of the Santa Barbara Astronomical Unit, South Central Coast Longtime Astrophysics and Telescope Club, based right there at the beautiful Santa Barbara Museum of Natural History, where we meet on the first Friday of every month. That'll be a week from this Friday for February. Nice speech delivered by Tim Thompson, I believe is his name, about Mount Wilson. And the SBAU's been around going on 70 years. And we're about to start our fourth year of doing this vlog when we reach March. This is program number 153. Vice President re-elected Ron Herron. I'll introduce you to the rest of the gang here in a minute. Welcome aboard from Monday, January 22nd, 2024 through the 28th. And then we welcome in February. Let's talk this week. And get this, we're going to talk about light cones, something I hadn't heard of before. We're going to explore the surface of the moon. It's going to go full by Wednesday. It's in a gibbous mode. In the Crab Nebula, we have the asteroid 4 Vesta heading for it. It's going to be near, and we're going to focus on it. Globular cluster M13 is, I guess in Hercules, right? It's the home of the Keystone asterism. More than 150 of these globular clusters dot our galaxy. Did you know that? Milky Way. Does the universe, ladies and gentlemen, have a center? Does it spin? Oh my God. It's like questions I come up with. And this, we got something sad to talk about at the end of our gathering here, how our sun's going to die and the stuff that made us up will be dying with it, I guess. We won't be around. The prognosis for the planets, but man, that light cones thing. Let's meet the gang. There he is in semi-darkness. Get in close, Jerry, so we can see your face under that beautiful pub.
Hi.
Jerry Wilson is our president for 7 years. And up until a few minutes ago, he was sitting in his dining room. Now he's out there in space, cruising around the Andromeda Galaxy. So President Jerry is married to Pat Forgy, and he was just recently reelected. Here's Chuck McPartland in front of the Ukrainian flag, our incredible outreach coordinator, who finally gave up secretarial duty to another gentleman who's not with us, but you'll meet him at star parties and things. That would be Andy. Chuck is married to Pat McPartland, our merchandise manager and our new treasurer. Bruce Murdoch is with us, longtime supporter, telescope enthusiast, knows his stuff, and president of the Santa Barbara Theater Organ Society. He's married to Bonnie. Tom Whittemore, former science instructor, there he is, Westmont College, edits our newsletter and bakes bread. And it's they're both damn good, except we don't get enough of the bread from him. He's married to Maureen. Yeah. Tim Crawford started joining us in this third year. Tim, expert, telescope, lens specialist, I guess a member of the Tuesday night workshop we have been doing. He's married to wife Karen. Tom Totten used to be with us. He's our webmaster. And we always start the week off on this 153rd episode with Jerry's forwarded silly science cartoons. There it is. You're going to have to enlarge this. The tree on the swing order. Here's how it all plays out in reality. We have the top line, what the customer described to the builder of the tree swing that he wanted, something totally dumb and impractical. What the bare-ass budget covered, not much more than a rope. What the engineer designed, wrong. Second line, how manufacturing installed it, totally unacceptable. How marketing advertised it, a comfortable swinging recliner chair on a rope. How it got documented, nothing. Didn't get documented at all. Bottom row, what the customer finally received. Get a load of how this looks. What he's billed for, something right out of Magic Mountain. And here's what the customer actually really truthfully wanted, a simple swinging rubber tire. Here are the two, I guess we have a cop on the moon, an alien cop. at the scene of an accident where a victim lying there is a cow. Let's see, he says, if I have it straight, you were cruising past the moon, right? Minding your own business when this cow suddenly jumped out of nowhere. I'm glad they finally resolved that silly little nursery rhyme. Speaking of nursery rhymes, here's Einstein's morning formula that we all kind of agree with. E equals mc squared, energy equals milk plus coffee times itself. My God, I have two
That means
cups
lots
of
of coffee.
Yeah. And here we have gathered around the table the four stick figures dining and something about, we don't have house guests very often, guys, one of the stick figures says, but we once had 6 astronauts over for dinner for about 7.5 milliseconds in mid-August 2012. The other lady at the end says, oh, wow.
Well,
See if
she
you,
said, "Oh wow," then he says 7.5 milliseconds,
Yeah.
is milliseconds, they're what, a thousandth of a second?
thousandth of a second.
Yes.
So it just passed over. If you spend
Yeah.
enough time looking at orbital records and property lines, they visit all of us, I guess, at some point. Or do they trace the same lines around the, never mind. Here's gnomes from hell, polynomial equation featuring 5 gnomes as opposed to Snow White's dwarfs. These are similar. All right, guys, they're in the math class. We won't solve this unless we all work it out together. 3k plus 4k squared plus 7 equals 0. That's a polynomial equation, huh?
Well,
This,
the roots are imaginary.
oh, okay. That imaginary raises its ugly head again. Now, I didn't get this when I first saw it. No, I'm not talking about the x minus y. Finally, today I looked at it and I realized there's a y and an x. But if you take the y away from the x, you get to the bottom right leg.
Yep. Of the X.
Okay. I would have gotten expelled from biology or algebra class if I'd said that.
It took me a moment too.
Yeah. Okay. Good stuff, Jerry. Here we have a milestone, the genius of Mr. Spock up on Star Trek, explaining to Captain Kirk some science. Get ready for a Tom Whittemore pun here. That's rather large, isn't it, Spock? Captain, sensors have just detected a meteor that's 5,280 feet in length. Yes, sir. It appears to be some sort of milestone. That's good. A little play on words.
It's a
And
groaner.
this one is going to need some explanation. It's a little scientific. The spinning stick figure apparently says, 3 lefts for going down the stairwell at work, 2 rights I did from cloverleaf interchanges coming to work, -1 for the Earth's rotation. Okay, that's a net of 17, right? And
17 to the right.
to the right. Okay, well, space-time health tip. Remember to cancel out your accumulated turns at the end of each day to avoid worldwide torsion. Is that like
line?
You turn so many times, you wound the Earth up. Now you have to unwind those same 2 times. It's like a joke back in the gas crisis of 77 or 76.
Right.
When they said we need to conserve energy. And so someone put in the Daily Bruin that we needed that conserving energy was only half the story. We needed to conserve energy and momentum. So every time you went anywhere, try to get a person of about the same mass to walk in the opposite direction.
Tim, did I introduce you?
I guess that didn't go over there.
Did I introduce Tim Crawford?
Yes, you did.
Yeah, you did.
I'm just seeing everybody's faces on the screen. That's a funny one there. I like that one. We should save all these or issue a book or something someday. Okay, we're going to talk about the moon and the fact that 3 of us are wearing hats, bringing them back, and looking forward to a great February. And this is winter in Southland, California. Well, actually, it's the monsoon season again. And there was a little bit of discrepancy with your notes, your talking points, as far as M13 and what's the other one there, gentlemen?
57.
Yeah, did you work that out? You want to work it out on that?
No, I didn't understand the email. We'll talk about that when we get to it.
Okay.
Well, it was just a typo in the caption on one of the images. That's all.
Okay.
Oh, was that all it was?
M5, they just dropped the 7.
Ah, well, you guys sure know your M's
Yeah.
and your NGQs and all that. Here we go.
M&Ms.
M&M. Wednesday night about 9 o'clock. It'll get full, but right now it looks full. And we're looking right at it.
You can't see it. even at night.
Oh, that's true. You're right. So why are we even talking about it?
Rain like
came down
hell.
pretty
Well,
heavy
it was last night.
Here
Behind the
anyway.
cloud cover. All right. There it is.
It's gonna be full, so we need
So
our
this
moon
one,
fan
this is
token.
your opportunity looking at the full moon to verify the optical illusion that when the moon first rises on the horizon, it looks very big. And 6 hours later, when you look at it straight overhead, it looks it looks much smaller. And but on the surface, there's no shadows that you can see or that are apparent. So you're really looking at reflectivity, albedo. And the thing that has the most is these ray systems from several craters where material was blown out on top of the surrounding. This one down here is Tycho. It's the most prominent one. And with all these rays going out, it always makes me think of a peeled orange.
Aha. That's the bottom or the
I've
top.
always wondered, Jerry, why the full moon displays these rays so vividly and not on other aspects.
I don't
One
understand.
reason is that the crystals or the minerals are tetrahedral in shape and they act as good corner reflectors.
Oh, okay.
So they reflect directly back. So if you plotted the brightness of the moon relative to the amount that was illuminated, at full, it jumps up like an extra 10%.
Oh, there you go.
So these crystals are like those little devices you see hanging off the masts of sailboats that enhance their radar reflectivity.
Yep.
Okay, good explanation.
And this is the wolf moon.
This is the crater Copernicus.
Okay.
And this is, I believe this is Stevenus. So those are the prominent features. They're nice craters on their own when there's a lot of shadows around, but you don't
That's
see the
Tycho
ray
right in
system.
the middle.
What's that?
Isn't that Tycho right in the middle?
This
No.
one right here, Tycho.
That's Tycho.
Wouldn't you see shadows in its circular horizon?
You can if it's not exactly full moon, you can take pictures along one of the limbs and you can just see some shadowed features on one side or the other.
Think about it, Ron. The shadows would be going directly away from you.
Yeah,
That's true. You're right. I know that. Okay. Wow. But we get all the Maoris on our side, the Chinese side, which I guess have they staked claim to the dark side of the moon, China?
no, the Russians did. The Russians were the first to photograph the backside of the moon. They, of course, everywhere on the moon gets dark at some times. But there's a crater Tsiolkovsky on the other side. They got to name everything on the moon that they could see. Their photograph wasn't that detailed, but there's a large crater on the back, smaller than this C, but it looks like a small C, and that's the crater Tsiolkovsky.
And there's also the Sea of Moscow. So there is a small Mare.
Yeah. But largely Europe labeled most of the near side.
Would it be fair to say that the reason the full moon washes out so much of the viewing at night is due to our atmosphere? If we didn't have an atmosphere, if it was like the moon down here and we were all in spacesuits, we could see the stars just as easily either way, right?
Yeah. Except maybe real near the moon.
Yeah.
Okay.
And the light would scatter off the faceplate of your spacesuit.
Yeah.
Well,
That's why they don't see a lot of stars when they're walking around the moon.
some of the doubters who say we didn't land on the moon and Apollo are using the fact that the pictures they sent back show no stars in the blackness.
Yeah, I've heard that.
And the reason for that is
The exposure was too short.
You know, a camera only has a couple of decades of exposure range because it's a linear detector. Our eyes can see what I think 5 decades of light. You know, I mean, you walk into a room with a window looking outside, and visually you can see everything. You can see the whole room, and you see it outside all at the same time. You try to take a picture of that, you can either get the exposure so you can see the window and what's outside, or you can see what's in the room and the window is overexposed.
well, this is a picture we're looking at, and there's no stars in it. So
Right,
Yeah.
because it was stopped down so it wouldn't be overexposed on the moon.
do they give the moon a magnitude?
Yes.
Yes.
About
It's
minus 13.
Minus 13.
Minus 13 at full. Yeah.
Okay, got it. All right.
Can I
The
just
sun's
take a
minus
second?
26, Ron.
It goes brighter, the more minus it is. It's amazing.
That's right. Yeah.
Can I
Okay.
So
just take a second?
the brightest stars are like 2.5 to the 12th power dimmer than the full moon.
Is that right? Wow.
Yeah, you're not going to
Tim?
see them in the same picture.
Tim,
Hey,
what did
yeah, Jerry, if people are watching, last week YouTube wasn't working because we had a problem with the Jerry's computer, and Chuck Watson's he's dialed it in. He let me know that he's he can see it now, so everything's working.
Yeah, I
Right.
talked to Tom, and we recorded it to the cloud, and so Tom retrieved it and put it on YouTube.
Okay, very good.
And before we went on the air,
Master to the rescue.
before we went on the air today, Jerry was broadcasting from his dining room, and now he's in front of the Andromeda Nebula. They got that worked out. Thank God.
Yeah, the air's kind of thin out here, but yeah.
And you need a light in your face, but maybe it's better. I don't know. Okay.
Okay, this is the constellation of Taurus. There's Aldebaran down here. Or is that it here?
that's it there.
That's it.
It's there.
The big guy.
Yeah. And here, down here, near one of the eyes, or one of the horns, I guess it is. The eyes are down here. Is Vesta.
Okay.
And so it's wending its way across here this week, this month. And it is something that we have visited by spacecraft. And this is a close-up photograph of the asteroid.
Huh.
Now, as I sent you guys, but I didn't show in this video log, an asteroid was found and predicted to hit the Earth over the weekend, and it did hit the Earth. It was about a meter across, it wasn't very big, and it came down just outside of Berlin in Germany. And
Can I point you out something about your notice, though, Jerry?
Yeah.
Here's what it says. NASA said a 3-foot diameter rock hit the Earth Sunday night, the 21st, which was yesterday. You sent this out Sunday morning at 11:02.
Yeah, but that's
okay,
universal time, Ron.
Yeah.
So we're talking about the difference in time between us and Europe. It's only about
And between Berlin and us.
Different time zones.
But it happened last night or 2 nights ago?
No, it happened Saturday night.
Saturday night. Okay. Then that would have been early 21st. Okay. Wow.
So so it I believe it exploded before it hit the ground, and
Yeah.
so people are madly looking for where for pieces of this. There's a lot of money in finding pieces of different asteroids and then selling them online. There are a number of people and museums that collect them, and a lot of people, if they're in good enough shape, they want to do composition studies on them. So museums and scientific agencies buy them. So
This asteroid is mainly mineral rock, not metallic.
We don't know what it was.
Yeah, we don't know yet. All we know, it was a bright light in the sky heading down.
It was probably stony because that's the major proportion of meteors are stony meteorites when they hit.
Mhm.
Well, it's hard for me to imagine that 5-pound sucker that's black that our outreach guy hands out to visitors to our second Saturday star parties could get burned up by just air, but it's probably the remnants of something like what we're looking at, wouldn't it?
It ram heats the air in front of it, Ron, and that gets to quite high temperatures because these things can be going 30,000 miles an hour, and that melts it and it ablates away. So that's what the burning up is.
So
you end up with lots of little spherules of nickel iron falling down to the ground. It's not like it disappears.
I got you.
Ron, you can take your hands. See, I got two hands here.
Right.
Rub them back and forth very fast. And what do you feel?
Oh my God, they're burning up.
You feel them getting hot from the friction.
Yeah, that's true. I do that some nights.
Now that's not moving anywhere close to the 30,000 miles an hour that some of these meteors hit at. So there's a lot of friction there. It melted a space shuttle.
Yeah. Well, it's
17,000.
It's not primarily the friction. It's the ram heating. The air gets compressed in front of it and heats up.
Right.
And then that transfers to it. And you end up with a thin layer getting ablated off, and the interior can remain cold. So often once they hit the ground, you give them a minute or two and they end up covered with frost, even though they've just come through, because they only spend seconds in the atmosphere, but they spend billions of years cold soaking in outer space.
Oh, that's really weird.
And ablation is the method that we use to cool the Apollo and Mercury and Gemini capsules with heat shields that as they got hot, the hot part snapped off and was thrown off, took the heat with it.
Well, the one that's reached the Earth are got to be a minimum size. We certainly know the one 65 million years ago was what, about 3 or 4 or 6 miles across that killed the dinosaurs?
About 6 to 9, yeah.
Okay, but the one in Tunguska, 1908, Russia, was
we
that?
Don't know because we're not sure of the composition.
Right.
That one exploded in the atmosphere, did it not?
Yeah, there was no single pieces of it found.
The Chelyabinsk one that happened in 2013 was 60 feet across. And the biggest piece they found on the ground was just 3 feet across.
Yeah, I think they found it in a lake. It went through the ice.
Yeah.
So the one over the weekend didn't survive. It totally melted or fragmented.
Fragmented. Yeah.
Yeah,
so
fragmented.
There might be fragments.
Interesting, fascinating stuff. Okay, where are we now?
Okay, well, since this is just before the full moon, the moon is pretty bright in the sky. Doesn't matter to us here in Santa Barbara because we're having a rainstorm. But if you want to look at things, this is the time to look at clusters, not things that are faint and fuzzy, because the moon's scattered light will wash those out. That's wash with an R. But this is the constellation up here. This is the constellation of Hercules right there. Okay. And this asterism is part of that constellation, and it's called the Keystone. What is it, a rhomboid or a trapezoid?
Rhombus.
Trapezoid.
Rhombus?
Well, it's got four sides, so it's trapezoid.
Okay. So if you look over here at the eastern edge of it, you can see these the curved, one of the curved sides, and 1/3 of the way down that line is where M13 is. It's easy to locate, and it's bright enough that you can get a really good view in an amateur scope. This is a photograph. Could be taken by an amateur, but because this is a very big and very bright object, it has characteristic lines in it, like this line right here, and a V-shaped darkness there that is called the propeller, I believe.
Yeah,
I recall. And there's also supposed to be a galaxy in the background, but
6207. NGC 6207. I think it's about 30 million light years back, something like that.
Yeah.
Good grief.
On a good night, I mean, you can see it with the 8-inch at Westmont.
Yeah.
Really?
Good night, though.
I don't know if that shows up in this picture.
I don't see it, Jerry.
Yeah, I don't either. Okay.
Yeah.
Must be just out of the frame because it's not that far from Cloudlet Cluster.
And star hopping, I always try to, tell people that if you're trying to locate M13 by star hopping, it's really going to be on that trapezoid. It's going to be on the side of that trapezoid nearest Vega. And that's where you want to look. So many nights I look on the other side and I'm going, where did it go? But
hey, Jerry. Jerry, I was going to mention a little trivia here if you want to hear it.
Sure.
So, I'm reading this really neat book for probably the third time called Lonely Hearts of the Cosmos. It's written by Dennis Overby about 30 years ago. And it's kind of the history of the cosmologists, in the 20th century. And it's not to our time, of course, 30 years old, but it focuses in on Alan Sandage, who was the understudy of Edwin Hubble, the fellow who discovered the expansion of the universe. And it turns out my connection is that you see that NGC 6341? We call it M92. We call it M92. It turns out that was the topic of Alan Sandage's dissertation at Caltech. Kind of interesting. I just learned that a few days ago.
Wow.
So that's the globular that Alan Sandage, who passed away a few years ago, lived a long life. Okay. But anyway,
Hubble,
that was his study piece.
Okay.
Okay, you said he helped Hubble, and Hubble did most of his work.
Well, he was an understudy of Hubble. Hubble died in the early 50s, and Allen just kind of took up his work. What Hubble was trying to do before he passed, remember, the 200-inch was just fresh in 1948, and I think Hubble died around 1952. He had a heart attack ahead of that. But what he wanted to do was to try to reach out to some of the more distant galaxies to see, in fact, if the universe was closed. Okay, so that was what he was doing. And so Sandage kind of took that on his shoulders and then ended up doing things with quasars and stuff like that in the 60s. It's a really neat book, if anybody's interested, called Lonely Hearts of the Cosmos. It's really about the personalities, all the personalities. Okay. It's really cool.
Okay.
We may hear about it on Friday night the 2nd and end of next week by our speaker on Mount Wilson, because that's about the only big telescope we had around the world 100 years ago, wasn't it?
Yeah. Yeah. So that telescope was dedicated in 1917. And in 2017, it turned out the Ellery Hale's grandson lives in Montecito near Westmont. And he had a group of people, it's really interesting, a group of people who wanted to have a little star show over at Westmont. And so we did it. And I didn't realize that this was the real Hubble. I'm sorry, Hale, George Ellery Hale's. Yeah, I think you were there, Chuck, right?
Yeah.
And yeah, it was really cool. Too. He's a really, really nice guy, really, really wonderful person. And that famous book on the 200-inch, what is it called, Tim? Acre of Glass, Tim, right? Acre of Glass?
That's one of them.
Yeah, he just loved that book. He just really loved that book. So anyway, there's a little bit of history and crazy story.
Acre of Glass? That's a hell of a large telescope.
Oh,
it's an exaggeration.
Yeah,
but the amount of glass that they removed from it in the initial grinding would really blow your mind. It was tons of glass.
The 200-inch telescope was an f3.3, so they started with a flat blank, so there was a lot of glass coming out of it.
That's a chunk of glass, Jerry. You're right.
Yeah. Okay, so globulars in general were not known to be clusters. They were until the large telescopes in the mid-18th century looked at them. Up until that time, they were just seen in small scopes like Charles Messier's, and they assumed they were just faint nebula, fuzzy spots in the sky. So
a glass telescope, if it were circular and 1 acre in area, would be 33 feet in diameter.
But some of these globular clusters look like they're outside the disk of the Milky Way, and that's the point, isn't it?
Mm-hmm.
Is that the ones we captured in small orbiting galaxies around us?
This graphic illustrates as a map of the location of globular clusters, known globular clusters around the Milky Way. This is the plane of the Milky Way, schematized. And these are going not in the same, if the Milky Way rotates this way, a lot of these are retrograde, they go the other way, but they don't rotate around the same angular momentum vector in here. These are in circular orbits around the core. So this one far out may just go down below and then back up. That is, they don't necessarily follow the pattern of the rotational pattern of the galaxy.
Like the orbit of Pluto.
The orbit of Pluto is inclined to our ecliptic, and these are inclined to the galactic ecliptic. That's true.
And their distribution was one of the first hints of where the core of the galaxy was.
That's right. Shapley.
Yeah.
Mm-hmm. Yeah.
But there's probably individual stars out there too. Could we see those occasionally?
Yeah.
Mm-hmm. They do, because some of these globular clusters are leaving trails and anti-trails in the orbit ahead and behind them. They do lose members as they go around, but in some cases very slowly. There is one that's prolific in shedding stars, and that one is probably near the end of its life as a globular cluster. But how they formed and where they formed is a mystery. This one shows 150 known globulars. There's probably around 200, because so much of the sky is blocked by the Milky Way that we can't see.
And
Wow.
these clusters, don't stick in the plane of the galaxy, and that's why open clusters, which do, were often called galactic clusters instead.
Okay. So these
You would-
are
one
believed
would-
to be, go ahead.
I was going to say, one would think the way the universe or the galaxy is laid out like that there would be a portion of the sky, not only that's bright, which is the angled look at the edge of the galaxy, but hardly anything there. But there is no, what are they called? Voids?
There are voids, but there is a void here too. You can see if you look at every one of these purple lines, they intersect the disk on this side of the center. There's nothing that intersects the disk on that side of center. And that's simply the fact that there's so much of the galaxy that blocks our view of what's out there.
But our little solar system is firmly ensconced within the disk, right? We're not above or below it, or
We're just a teensy bit above, I believe.
Well, we wander. There's a sine wave motion that we make, so
Right.
we're higher sometimes and lower at other times as we go around.
right.
But it's
The
like a
orbits of
200
stars around the disk are not, they're approximated by, but not accurately represented by a single point source of gravity. This is a distributed source with a center.
but it seems to me globular clusters are almost like little mini galaxies of their own, aren't
exactly.
they? Exactly.
Yeah, that may be one of the places, their sources. They might be leftover cores of very rich star-forming galaxies that do not exist today.
Well, you would think if two big galaxies like Andromeda and Milky Way were to collide, there'd be some major collisions involving these damn spots we're looking at here.
Now,
If they got close
remind
together.
yourself of why space is called space.
But there's 100 million. What did you write, Tim? You said something about one of those globular clusters. It wasn't 100,000. It was 1 million. That's exactly what you.
Yeah, but Jerry's taking. He wrote me back and he said that he's getting information from Wikipedia, and that number is really so. It's so debatable. The people in the star parties, they always come up to me and say, "Well, how do you know there's 1 million?" And I said, "Well, they paid some guy minimum wage to count them." And the first night was okay, but the second
It's below
night
minimum wage. They're grad students.
Yeah, and it said the second night was tough because they couldn't remember where they left off.
Yeah, right. Had to start over.
Okay.
So there are no known globular clusters that display active star formation. They all have no dust in them, but it's believed that for that population of stars like that, they came from a superstar cluster with very active, more than we normally see, star formation. And the closest galaxy, or not galaxy, but star cluster to what is hypothesized as a source of a globular cluster is called Westerland 1, which is very hard to find on this.
So clusters aren't the result of a nebula.
No, they are.
No, they are the result.
Stars start as nebula.
Okay, and all the dust gets swept up and becomes stars, and that's so from nebula to star cluster.
Yes.
Globular cluster.
Now we're looking
nebula is
at-
a very generic term, but yeah, star forming nebula to stars.
Wow. Okay. Dazzle me more here, Mr. President.
Okay. So this is the rough position of, but it's not marked as any of these NGC numbers, as where Westerland 1 is. This is south of the border. We're at declination minus 45 degrees at right ascension 16 hours.
So this would
we're not going to
just
see that
barely skim our horizon.
Right. Yeah. Yeah, the
And
edge
this
of
is
our
a
horizon
photograph
is about
of-
minus 56.
This is a photograph of Westerland 1.
Wow.
So we're only talking
It's
about
a very, very young massive star cluster in our galaxy. The
And
image
Ron, you'll like
consists-
it. That star in the lower left there that's really bright is a magnetar for you.
Yeah,
On the lower left?
Yeah.
Okay.
right there.
We've talked about magnetars, but that's a rare star that just has a heavy electromagnetic field around it for some reason.
Now this is from a Atacama Large Millimeter Submillimeter Array, or ALMA, and this Hubble Space Telescope. It's a combined microwave and or large millimeter submillimeter date light and red image.
But it is a cluster, and it's not a million there, I don't think.
It is a cluster, and there's some gas in here. You can see the red stuff smeared around here. It's dense enough that this is, if there's a candidate that we can find for a future globular cluster, this is considered to be that thing. It is looked at through our galaxy. There's a lot of dust. So this is what it looks like in straight visible light.
Very reddened.
Yeah, very reddened. And on right is an X-ray wavelength picture of the same thing. And this star down here is the magnetar.
Huh.
God, it almost looks like it swam right through that. It has a path going right through what do I want to call it? Just a cluster?
Oh, like the magnetar came out from the bottom and left a trail?
Yeah, yeah. Or it came up
There's
from
kind
the
of
top.
an S-shaped asterism here that implies some kind of a rotation, galaxy-like rotation. But you'd have to know the velocities of these things in order to really make any statements like that of what the orbit is.
But they say that this could be a source, or a not a source for globulars, but a candidate for how they're formed.
Yeah, a candidate for becoming a globular.
Okay,
Right.
That's so interesting.
Well, how do you suppose science discovers that that's a magnetar? Can you see magnetic waves with some of these exotic telescopes? Is that
If you look,
sort of.
if you look at the visible light, you can see effects, polarization, and so on from magnetic fields.
Right.
That's how they map the magnetic fields of the sunspots on the sun.
Oh, really? Okay.
But the fact that the left side picture are all red, that doesn't mean they're going away from us faster than coming.
No. That's dust in between us and them reddening the light by scattering the blue light.
Oh,
But it's still infrared, right?
No, that's a visible light image.
Yeah.
Well, that's visible light, so we're not looking through the dust, and it didn't.
We're looking through the dust.
Did it require the Webb to get this picture?
No.
No, that's not a Webb picture.
Oh,
ESO, European Space Observatory, right?
Yeah, ESO.
European Southern Observatory, yeah.
Southern Observatory, okay.
ESO. And this is Chandra, X-ray satellite.
wow. Magnetars fascinate me. I wonder if they had all metal planets that would be orbiting just because of.
You wouldn't have any fillings in your teeth if you were there.
or iron in my blood, I've heard.
Yeah.
ooh, ooh.
Yeah, that would be awesome. That would be.
That's a nasty thought.
I'm sure that's been portrayed in some science fiction story.
Or will be.
Or will be, getting too near a magnetar.
There is a silly reference to that in one of the X-Men movies, if you've seen those things where mutants have special powers. One of them can manipulate ferrous metals, and he mentally manipulates the iron in a guard's blood in prison, pulling it out of his body and killing him, and he makes things out of it and breaks out of jail.
Do you suppose Mother Nature put the iron in our blood, and probably all animals, or at least mammals' blood, because it takes the oxygen and bonds to the oxygen atom?
It carries the oxygen, and it holds it with a weak enough bond that the cell can pull it off when the blood gets there.
It's the hemoglobin.
Yeah.
It's not just iron, it's more complex than that, but it contains an iron molecule or an iron atom.
I stepped out for a minute because I was real curious when Tom was talking about the acre of glass. The book I remember, Tom, was The Perfect Machine.
Yeah.
Oh, that's it.
Ronald Florence. Yeah. And that's
the book
all about the Hale telescope.
Yeah. So, yeah, Sam Hale mentioned that book and he loved it. That's right.
The Perfect Machine. Yeah. And there's another one called Palomar by Helen Wright, who was a personal biography for Hale. I'm kind of wading through that now. But anyway, just a comment. I went looking for it. I couldn't remember the name of it.
Where is the Hale scope?
Palomar.
Palomar.
It's the 200-inch.
Where is it?
San
In
Diego.
It's San Diego
Palomar.
area.
Yeah,
Okay,
it's northeast of San Diego.
You drive
Yeah.
to Temecula and then you drive east.
all right. I know about the mountain range. Little Julian is
And
probably.
if you drive up there on a weekend, you're going to play chicken with motorcycle after motorcycle that are doing these kind of road races on the wrong side of the road coming downhill.
Oh
They
God.
don't do it more than once.
I got you, Hale. The Keck is in Arizona, right?
No, the Keck is in
It's in Hawaii.
Montecito and also in Hawaii.
And in South America.
Yeah.
Wow.
There's the thing about iron, you know, these authors want to say, well, it's going to pull the iron out of your body. Iron has a feature called saturation. And for steels, for example, it's about anywhere between 10,000 and 15,000 Tesla. And above that magnetic level, the iron loses its magnetic ability.
Hmm.
So, you know, you can be in a very intense magnetic field, like going into a CAT scan machine. I'm sorry,
MRI.
MRI. And even though it's a very intense magnetic field, several Tesla, it, you know, the iron in your blood and whatnot just saturates. It can't get any more magnetic than it's allowed to physically.
Well, the big thing about iron, which is designated Fe, is that it's the level that ends a star. It's over for the big star.
Yeah.
Yeah.
End of the
26.
line.
That's
So-
the beauty of.
This is a representation of the universe from the very beginning of the bang at the start here.
Yeah.
And present time is this outer rim here where you can see galaxies and stuff. And these are the various stages of reionization and microwave background. It's just a graphic. It's not a photograph or anything.
Right.
But it represents, in a way, the misconcept that the Big Bang was an explosion of matter or energy. It's not. The actual thing that is produced in the Big Bang was a sudden outflow of space-time. Space-time, it's not stuff in space-time that exploded. It was the actual space-time.
The
And
fabric,
what's that?
the space-time fabric.
Yeah, the fabric of the universe. So
Well,
it's not a backdrop. It's an actual thing that can be measured. It has shape, it can be bent, and it can expand, and it can support waves. So it is an elastic media, and it has about 10,000 times the response or the stiffness of steel. It's what we all live in, and it is expanding into what? Probably nothing. The idea that it has a center and an edge is because of the limited way that we think in terms of calibrating our brain in everyday experiences. The universe go ahead.
I always tell people that everybody is the center of their own universe because
Yes.
everywhere the Big Bang happened everywhere, right? Everything
Yes.
used to be in one place, sort of.
Well,
And so I always tell kids, well, you're the center of your own universe, just like most teenagers think, because you can see, 13.8 billion years in that direction, and I can see 13.8 billion years in this direction. And if you're a foot away from me, you can see a foot farther in that direction, and I can see a foot farther in this direction.
Right.
So everybody's the center of their own universe.
Well, that's the apparent universe,
Yeah.
the visual universe.
well,
But
if the Big Bang was just the space time, where did the matter come from?
All the energy that was in there.
Energy.
Energy.
so Astronomy Magazine makes the analogy to a balloon. You remember the bread dough with the raisins in it and stuff?
Yeah.
But now we're doing a balloon.
Well-
Because the balloon has a two-dimensional surface and it encloses a three-dimensional space in which creatures live. We are 3D creatures in a universe with at least 4 dimensions. So we cannot see the center of our universe. In fact, there is no reason why there has to even be a center anywhere. We live on the surface of a 4-dimensional balloon. So we cannot detect any center. We also cannot detect the edge. So we live on the edge. We live on a 4-dimensional edge.
Well, can I bring up something? The analogy of the raisins and the bread, and this may touch a nerve with Mr. Whittemore because I'm not sure if he makes raisin bread or not.
I sure do.
Couldn't science, by looking at this expanding loaf with the raisins all going apart, they could pinpoint eventually by knowing which way this raisin's going and on the other side this raisin. They could find the center.
Run. It's an infinite loaf. Consider it an effectively infinite loaf of bread. And if you're sitting on a raisin, you picture yourself as standing still and all the other raisins are moving away from you. So you look like you're the center.
It's like when you're standing on a balloon and you blow it up.
Yeah.
Everything goes away from you in any direction.
I wrote
when they ask the question, the edge of the universe, what's at the edge? That connotes to me something.
No, it's a conceptual problem. A creature that is one dimension lower than the dimensionality of what he's in cannot see a higher dimensional edge.
Go read the book Flatland.
Yeah, that's a good place to start.
Once Alex Filippenko visited at the museum, and I asked him, where's the center of the Big Bang? And he had his famous little balloon out and blew it up. And he said, well, it's at the center of this balloon, except it's not there anymore. And everybody was going, huh?
Yeah.
I think, Jerry, you hit it when you said it's conceptually that when we try to visualize this stuff, it doesn't work.
Yeah, that's right.
But Jerry, is your analogy of the balloon, is that a 2-dimensional, meaning the things that are on the surface of the balloon, or is it filled completely and therefore 3-dimensional?
The balloon is 2-dimensional surface in which 2-dimensional creatures live, but it's a 3-dimensional object and it's expanding in the 3rd dimension, which also makes it expand in the 2 dimensions. But if we were inside that balloon, we could probably figure out where the center of the balloon was.
You're not inside the balloon. You're living on the surface of the balloon. You're 2-dimensional.
Okay, but I'm not. We're in a 4 dimensions.
Right. Now you got to expand to the next higher analogy. We see things as though it's 3-dimensional.
They do a nice analogy of a 2-dimensional creature in a 3-dimensional universe. And the one person that's reporting is a 3-dimensional person, and they see the 2-dimensional flatlander of a flatland object like a circle comes into their field of view. It just gets wider and wider, then narrower and narrower, and then it goes away.
Yeah, you need to read Flatland for the analogy he just referred to.
By a fellow named Abbott. It's a really good book.
Yeah. So the other last does it have a center? Probably no. Does it have an edge? Probably no. Does it have spin? Many things spin. So the one school of thought is that if the universe had spin, it would eventually over time break up into minor, everything would not go, the big spin would break up into eddies, little eddies. And so we would have to find that residual eddies. And you keep asking this about whether all the galaxies are rotating the same way and all pointing the same way. And it's about 10% yes. About 10% more galaxies are left-handed spirals spinning in the same direction as our own. But that's only a slight difference. It's not proof positive. But it does, to some people, it does suggest that the universe as a whole once had a net spin to it. But it's a very, very small spin if there's any residual to it.
Well, is there any depth to the thought that there are multiverses, many, which would lead me to think that they're all cells, and therefore they would have to have.
We're not discussing metaverses in this discussion.
But they would be in other dimensions, Ron. So
yeah.
Well, I know, but the quantum people have come along and said we have as many as 11 dimensions. What the hell?
Some people, not quantum people, but people doing
String theory.
String theory, thank you. They need to prophesy multiple dimensions and multi-universes in order for their theory to work.
Oh, no kidding, really?
Yeah.
We
So
can't just
this is an example that they show of the Gemini Observatory image of a cluster of galaxies with their rotations that they use to illustrate the slight discrepancy of spiral image or spiral preference.
Huh.
Yeah, there's two galaxies in that picture, one of which is rotating clockwise, the other anti-clockwise.
That you can't tell from the way the arms go.
Oh, that's right. Yes. Because gravity doesn't work.
Well, apparently not very well there. Not
Because
intuitively.
of dark matter.
It does work.
Well, that dark matter thing has to do with the rate of rotation, not with the direction.
Yeah.
Is this our sun?
This is our sun, taken recently at an observatory. It's quite nicely processed. A lot of prominences. And what happens is we have a ordinary middleweight sun that has been, it's about 4.6 billion years old, and it will eventually run out of hydrogen in 5 billion years or so, and it will swell into a red giant. This is our sun here on a Hertzsprung-Russell diagram. Hertzsprung-Russell. This is a star's luminosity, that is how bright it is at a fixed distance, so we can compare all of them. And this is the surface temperature of the star. Ours is here about just slightly under 6,000 degrees Kelvin. And it will, when it runs out of hydrogen, it will then expand and swell and join this group of red giants, and it will exist here for a while. And as it slowly loses or goes off to the next stage, then it will go through this instability. It'll cross the main sequence again into an instability strip up here, where it will be a variable star, such as Betelgeuse is now. Betelgeuse is much bigger than our sun, so forget that analogy. Then it will fuel gravitational collapse, because now there's no fusion going on in the center to resist the gravitational collapse without going photons. And it will collapse into the group down here, which is various types of white dwarfs. And that's where it will end up. When it goes up here, it will expand out to the past Venus and to about the orbit of the Earth, maybe a little farther. But in doing so, it will be 10 billion years old by that time, and it will have lost mass because of its solar wind going out. So as its mass decreases, the amount of its hold on the planet, the gravitational hold, weakens. And so the Earth's orbit may move out. So it's an open question whether it's going to move out far enough to not get included in the sun or get included. In any event, the sun will have boiled off the oceans by then anyway. So even if the Earth as a whole survives, there won't be any life on it.
So most of the fusion is happening in the center of the sun. That's where the hydrogen becomes helium or lithium. Where are all those other elements that are everywhere in the solar system that became us?
They don't come from our sun-sized stars.
But they're in there with the hydrogen, I would think.
Yes, but they're just tiny contaminants, Ron. It's just a little scum of other stuff.
Really? Even though
it's like 99% hydrogen.
Okay, and that hydrogen over the millennia, the billions of years, until it finally gets to fusion to something, it's just in a state of flux, and this plasma never fusing, just like extreme burning, just moving around, staying hydrogen atoms.
Yep.
Until its time comes in a few billion years.
Well, it has to be in the core. A lot of the hydrogen in the sun is just going to get puffed off. It's only the stuff in the core that gets fused into helium.
Okay, so that fusion is not taking place where we can see it at all. It's just
right, way down in there.
Gone by then. We've been cooked.
It's down in the basement.
Okay,
so this is, and then it will form, and going back up here, as it throws off its atmosphere down here, it will become a white dwarf, the star will, but it will also form a planetary nebula. This is a planetary nebula M57, incorrectly labeled as M5. I left the 7 off.
Yeah, M5's a globular.
Yeah. So, and this is taken by the James Webb, and it is an incredibly detailed picture.
Wow.
And there's the center star, the white dwarf. And this is well inside of the crap that it threw off.
But no, they say this has nothing to do with planets. It's called a planetary nebula, but isn't the remains of a lot of planets that might have circled that star at one time in the middle of all that morass we're looking at?
If they circled the star, then yes, there's some planet crap in there.
But that's not the reason they call it a planetary nebula.
No,
They're called planetaries because our eye is more sensitive to green light, and there's fluorescing oxygen in here, and that gives off green light. And when these things were first being observed carefully in the 1800s, they saw the green light more prominently, and that they had just discovered the planets Uranus and Neptune, which look greenish blue. So they said, these are clouds that look like planets. That's how they got that name.
But
yeah,
that's
the word came from using economic telescopes.
Yeah.
So right there, we're looking at our own solar system in about, what, 5 billion years?
5 to 7,
5
yeah.
billion, yeah. Here's another close-up of a
It's the Owl cluster, isn't it?
Owl Nebula.
yeah, the Owl Nebula is from the Pine Mountain Club here in
Oh, wow.
California.
Yeah.
And it was taken with a 600 millimeter Nikon lens on a CCD camera with filters, various filters, LRGB filters, hydrogen alpha, and O3 filter, and blended together to give this mix of false colors.
But now what we're looking at there, would that have been about the same size as the stellar system that at one time existed, or would that have been really tiny in the middle of all of this? Way
Really
out
tiny. These things are light years across, some of them.
Oh.
This is the 27, this is the Dumbbell Nebula with also taken by amateurs from the Pine Mountain Club with the same camera, Nikon camera lens on a QSI 690 CCD camera. With
Isn't that interesting, the coloration? Wow.
Yeah.
And that bright part you see there is about 2 light years across on that.
Wow. Dumbbell because of the shape. It could also be butterfly shaped.
Apple core.
Apple core.
Yeah.
Apple core.
I like that. Is there an apple core nebula out there?
No.
Right there.
Well, that's,
When you look at this nebula in our scopes, you don't see all the very dim stuff. And it certainly much more resembles an apple core than it does a dumbbell.
Yeah, the bright sort of reddish pink stuff you're seeing here is the stuff that you see visually in a small scope.
Yeah.
I got to tell you, Mr. President, we're talking light cones, or you want to put that on the future calendar, because here it is. We got 3 or 4 minutes to talk
It's
about.
it's a longer discussion because it's subtle, but it's very easy.
Okay.
We'll briefly do the light cone, and then we'll talk about curve space light cone from next week. But you are here. This is time, and so and this is space. So as long as you don't move, you're sitting in front of your computer screen. You are moving up this axis, and these lines here are at 45 degrees, and that is the speed of light in this space. So things that happen in the future have to happen on the light cone for you to see them. If something happens out here, the light starts from there, but you can't get to it.
It would start another cone, and where that cone finally intersects with yours is when you would see it.
Yes. So this is you going up here. So this stuff up here is time light. Stuff down here is space light.
Wow.
And this was suggested by Minkowski and I working with Einstein as a method of describing certain solutions to Einstein's general relativity case. And just as a treat coming in, this is in curved space, and this is of a collapsing star, collapsing down to its timeline goes up here, and it's a singularity. Mathematical singularity doesn't mean there's a real singularity. And these are the light cones of observers nearby. And as you see, space is curved, so their timeline is curved, and they are eventually going to enter and merge with this timeline. And so their light cones start tipping over as we go up. So we'll discuss that more next time.
Yeah, please. This is really confusing me.
Well, I certainly got it. What's wrong with you
I've got a
guys?
headache. I need chocolate.
Made sense to me. Singularity has another way of meaning. It's not just around a black hole. My God.
Okay.
But it's fascinating stuff. Mr. President, your lovely wife, Ms. Forgy, is going to have to get you a light so we can see your handsome face.
Oh, we're redoing my whole office here, so
That's all right. There you go. See how
the place where I sit in my bedroom where I'm better lit.
Yeah.
The cleaning lady's here today from
I got you.
11 to 2 or something.
Well, I really like your look in a Santa hat because you do look the part, and so do I, damn it. But we're going to plunge ahead. God knows the stuff we'll be talking about next week, same time when we do program number 154 of the SBAU Astro Hour. Thank you, gentlemen. Take care of yourselves.
Thank you. Super interesting.
Yeah, pray for a clear sky.
Yeah.
No more cancellations. But I guess, is this Friday, Westmont?
No, that was Friday already.
It was canceled last Friday.
Yeah.
Oh, it was canceled last Friday.
Yeah, yeah.
Missed it.
Well, we're a week and a half.
Enjoy that sky window, Tom.
Yeah, tomorrow there'll be a little window.
All right. Well, we look forward. We do it if the clouds aren't there. We do that. But enjoy the monsoon until it goes away. We can.
Okay. Bye-bye.